If we draw a Venn diagram showing the sets A and B, we have the set A, we have the set B. Okay, we have a cardinality of A, which we're going to call N of A, a cardinality of B, which we'll call N of B. And we have some number in the overlap in A intersection B. Then what we're saying is that the number in A union B, which is the number we get when we lump all the elements, we count everything that we've got in these two sets, is the number that's in A, number here, plus a number in B, number here, minus the number that's in the intersection, because if we add these two numbers, we're counting the intersection twice. Now let's say that we had a situation where we knew those numbers, and let's just make up some numbers. Let's say that we have 12 elements in A, 16 elements in B, and that in the intersection we have, let's say, 5 elements. So how many elements do we have altogether in the two sets? Well, think about it now. If we have 5 here and 12 here, we can conclude that there must be 7 right here. There are 12 in the whole set A, and I haven't labeled that as A. Maybe I should do that. Okay, here's a set A, here's a set B. There are 12 elements in A, 16 elements in B, 5 in the overlap. That leaves 7 elements in A that aren't in the overlap. And how many elements of B that aren't in the overlap? Figure that out before I write it down. There are 11. Now how many elements does that make? That makes 7 plus 5 plus 11, right? So we can say that the number in A union B is 7 and 5 and 11, which is 27. If we add the number in A to the number in B and subtract the number in A intersection B, what are the numbers? Well, that gives us 12 in A, 16 in B, minus the 5 that are in the intersection. And again, that equals 27. We get the same thing either way. Now, this ability to deduce numbers can be important, and we're going to see that in this example. Okay, suppose now that we have 3 sets, A, B, and C, and we have some information on what's in different parts of A, B, and C. And we're going to draw a Venn diagram again. Okay, let's draw the 3 sets. A, B, and C. And then let's collect our information. Okay, there are 12 elements in A, 19 in B, 16 in C. So we're going to say 12 elements in the set A, 19 in the set B, (16 in the set C. And we'll just label that by some little arrows. Okay. Now, we also know that in A intersection B there are 10 elements. Now, where's A intersection B? Well, A intersection B consists of this region and this region. So the total in these two regions has to be 10. Now, we don't know how that divides between this region and this region, and we're ultimately going to want to figure out how many are in each of the 8 regions of this diagram. So what we're going to do is we're going to put the 10 here on the boundary between these two regions, indicating that that's the total of what's in these two regions, but we don't yet know how that breaks down. And A intersection C, where's A intersection C? Well, A intersection C is this region, with this line cutting it in two, so that if there are three elements, we're going to put a 3 on this line. And B intersection C consists of this region where B and C come together, and again a line in the middle of the region, and we're going to put a 6 right here to indicate that there are 6 elements in this region. And finally, A intersection B intersection C, there are 2, so we're going to be able to put a 2 right here in the middle. Now, can we determine how many are in each region? Could we determine how many in this region? We've got 19 in B. What about this region right here? Well, we know that there are 2 in this region, and we know that between these two regions there are 10, and between these two regions there are 6, but we still haven't figured out how that breaks down, so we don't really know how many there are in this combination of regions here that help to make up B. However, if we do a little deductive thinking here, if there are 10 here and 2 here, I guess if the 10 represents what's in these two regions and there are 2 here, that's going to leave us 8 out here, right? And if there are 6 between these two regions and 2 in this one, I guess that leaves us 4. And 3 between these two regions with 2 here, that leaves us 1 out here. Now we know that there are 8 and 2 and 4 in these 3 regions, and that adds up to 14. So that what we're going to have here is going to be 19 minus the 14 that we've got in these two regions, or 5. So we have 5 in this region. Now what do we have here? We have 8 and 2 and 1 is 11, and there are 12 in the set A. That's going to leave us 12 minus 11, or 1 element in the set A. Because again, the 8, the 2, and the 1 help make up the 12 that are in A. They all count as part of A, and that leaves us only 1 more element in A. Similarly, the 1, the 2, and the 4 are counted as part of C. 1, 2, and 4 add up to 7. So we have 16 minus 7, or 9, left in this region. Okay, that kind of reasoning then allows us to determine, for example, the number in A union B, A union B union C. Let's see where the number in A union B union C is then what? 1 here, and 8 here, and 5 here. Another 1 down here, a 2 here, a 4 here, and a 9. And we can add those up and determine how many we've got total. Notice that we don't include the 10, the 3, or the 6 because those are combined populations or combined numbers in more than one region. The problems you'll have in the text might give you even a little more information, like how many people there are total or how many objects there are total. And of course you'll have to interpret some applied problems, but you have several examples, and hopefully you'll be able to do that or ask questions, and I'll help you do it.